Hi learners, welcome. In this session, I am going to explain crystal field splitting of d orbitals in octahedral environment. Okay, so let's see. Points wise, I will explain. First thing, you have to know how the ligands are approaching. So this crystal field splitting, we are talking about the complex. So complex means metal will be there and ligands will be there. It's a general complex where the metal is surrounded with 6 ligands. Then in octahedral field, how the ligand approach towards the metal will be. That we have to see first. And let's take the structure for that. In this way, the 6 ligands are surrounded by the metal. And if I draw axis, then I will understand how the ligands are approaching. So I'm going to draw the axis here. Let's say X, Y and Z axis. If you see, all the ligands in octahedral complex are approaching towards the metal through the axis. You can see they are lying on the axis. So here the ligand approaches on the axis. Next thing is, that's about ligands first. Next thing is, we have to know about the metal d orbitals. There are 5 metal d orbitals. They are dxy, dyz, dzx, dx square y square and dz square. If you see the orientation of their lobes of all these orbitals, whenever you say, if you write like this, you can say they are said to be degenerated. Degenerated means having same energy. They are all having same energy. Okay, now in this, if you see the shape of d orbitals, 3 d orbitals are having lobes in between the axes. They are dxy, dyz and dzx. Okay, can change their axis x, y, z, z, x. Okay, these 3 orbitals belongs to one set. We call them as T2G. We call them as T2G. T means triply, G means gerate. Here all these 3 orbitals are having lobes in between the axes. You can see their lobes are present in between the axis. And the rest of the 2 orbitals are having lobes on the axis. For example, we take dx square y square. This is x axis, y axis. Similarly, d z square. And these two belongs to one set of orbitals because their lobes are lying on the axis. You can see they are on the axis. We call these two commonly as EG. Okay, there are 2 sets of orbitals, d orbitals with the metal. 3 of them are having lobes in between the axis and 2 of them are having lobes on the axis. We call them as triply degenerated and doubly degenerated. In general, if you take a free metal ion, all the 5 d orbitals are having equal energy. Then we call it as degenerated orbitals with equal energy. Now next, this about second point. First point I discussed about how the ligand is approaching in octahedral field. Next we discussed about what is the d orbital and how their lobes are lying within the metal. Next, third point, let's see crystal field splitting. Crystal field splitting. This is the energy axis where the metal has 5 degenerated d orbitals here. Okay, they are all having same energy. You can see on this energy axis, this is energy axis, and this is in case of free metal ion. Whenever the ligands are started to approach towards the metal to form the complex, and when they are far away, so it creates a symmetric crystal field on metal. Okay, so due to those symmetric crystal field, the ligand, the energy of metal d orbital slightly increases. You can see the energy axis here. The energy of d orbital slightly increases, but still they are all having equal energy. Again, degenerated d orbitals when in presence of spherically symmetrical field. Spherical symmetric field. Now when the ligands furtherly approach to the metal to form the complex, there will be repulsive forces between metal d orbitals as well as ligand electrons. Okay, because of that, say all 5 d orbitals of the metal won't get equal repulsive forces, because few of them have lobes in between the axis and the rest of them are having lobes on the axis. Because of this difference, this EG set of orbitals used to get more repulsive forces. Why? Because ligands are approaching on the axis and these orbitals are having lobes on the axis, and between these two there will be strong repulsive forces. Because of that reason, these 5 degenerated orbitals undergo splitting into 2 different energy levels. And the one that is having lobes on the axis, EG set, used to get more repulsive forces, whereas the other set, that is T2G, whose lobes are in between the axis, used to get lower energy. They occupies, this is the energy barrier, and the EG set is going to get higher energy, whereas 2G set is being stabilized here. It is destabilized, whereas it is stabilized. And if you see the energy gap between these two energy levels, it will be indicated with delta octahedral, that is equal to 10 dq. dq means distortion coefficient. And here if you see the energy from energy barrier to EG set, it will be 0.6 or 6 dq, and here it is 0.4 delta octahedral, or it equal to 4 dq. Okay, so you need to add these two in order to get total value. That will be 1 delta O, that equal to 10 dq. Okay, that is called crystal field splitting energy. Crystal field splitting energy. Now the next point is how to fill the electrons in this splitting in these energy levels. These are dxy, dyz, dzx orbitals, whereas these two are dx square, y square and dz square. We call it as, and here 3 orbitals are degenerated, and here only 2 orbitals are degenerated. Triply degenerated, doubly degenerated. Now when you want to fill the electrons in these energy levels, you have to consider one more point, that is whether the ligand is a weak field ligand or a strong field ligand. Let's see. Whenever a ligand is a weak field ligand, the splitting will be same. There won't be any difference. But the energy gap between T2G and EG will be very less. You see, this is the delta O in case of weak field ligand. If a ligand is a weak field ligand, then the energy gap between T2G and EG will be very less. So that's the reason why here we need to fill electrons by following Hund's rule. First you have to fill T2G and EG should be half filled, followed by you have to pair up. Whereas in case of strong field ligand, you can see the energy gap between T2G and EG is very high. So that's why electron can't go immediately to EG level after half filling T2G. First you have to completely fill T2G, means you have to pair up the electrons here, and after that still if you have electron, then you have to go to Eg. I will explain by taking one example. This is in case of strong field ligand. I am going to take an example, that is okay. In both the cases metal is same and it is in +2 oxidation state here, and here also it is in +2 oxidation state, means it is in D6 system. It is a D6 system, but the only difference is here it is a weak field ligand, it is a strong field ligand. So now how to fill the electrons whenever a ligand is a weak field ligand? As I said, 6 electrons are there, 1, 2, 3, and after that you have to go to the next level, that is Eg, 3, 4, 5, and then come back. 6 means what? First you have to fill both T2G and Eg, half filled. After half filling both the levels, then only you have to pair up. Okay, but in case of strong field ligand, how many electrons we have? 6 electrons. First half fill the T2G, then because of large energy gap, the electrons can't go to Eg level. So instead of that, they undergo electron pairing. Okay, all 6 electrons are filled in T2G. Each orbital will have it can fill 2 electrons. So all 6 electrons can be filled in T2G. So that's the reason why you see here it has spin free electrons, so it acts as a paramagnetic in nature, whereas it has completely paired electrons, it acts as a diamagnetic in nature. So in order to explain crystal field splitting of the orbitals of any of the complex, you have to explain in this way. You need to consider how the ligands are approaching in the particular complex. I mean that is it octahedral, tetrahedral, square. Each geometry will be having different approach. Here we discussed about octahedral, so ligand approach is on the axis. Next we have to see about the metal d orbitals. Metal d orbitals can be taken into two sets, T2G and Eg, because T2G means they are having lobes in between the axis, whereas Eg set is having lobes on the axis. Next, if you see the ligand approach, in terms of the ligands, there will be slight increase in the d orbital energy, but still it is degenerated. But when the ligand comes very close to the metal, because of the repulsive forces existing between metal d orbitals and ligand electrons, 5 degenerated d orbitals undergo splitting into 2 different energy levels. One is having 3 degenerated levels, the other is having 2 degenerated levels, and that's the third thing. This is called crystal field splitting. And the fourth case is how to fill the electrons in this crystal field splitting. So depending on whether the ligand is a weak field ligand and strong field ligand, you have to fill the electrons. If it is weak field ligand, first you have to half fill all the 5 energy levels, then followed by pairing. If it is strong field ligand, first you have to pair up in T2G, and if you have any remaining electron, then you have to fill in Eg. So that's about the first crystal field splitting in octahedral complex. So thank you for watching. Please subscribe to my channel for more videos.